Good morning, students. Today we are going to discuss partially miscible liquid pairs. Okay, partially miscible liquid pairs. I have already written in the board. You know, we have already done the practical and you know little bit of theory about it. At the same time, what we did is that we experimentally we drew the phase diagram of phenol water system. Today we are going to discuss partially miscible liquid pair in detail with special emphasis on phenol water system. Okay, so what do? You take water in a beaker. Suppose you have taken water in a beaker and you are adding phenol gradually. What you see at first? Phenol dissolves in water, giving an unsaturated solution. Okay, and you go on increasing the addition of phenol, and a time will come when you see that there are two different layers or two different solutions. What are they? They are basically saturated solution of phenol in water and saturated solution of water in phenol. So you look at the diagram. Suppose we are here. This is the temperature versus percentage of phenol composition diagram, and we have kept the pressure constant. In our previous classes you already know that for a two component system the maximum F is 3, and for drawing a three-dimensional phase diagram in a two-dimensional paper a little bit easy, it will be tedious. So what we do, we keep the pressure constant, and thereby the maximum degrees of freedom for such systems become 2, and it is then convenient to draw the phase diagram, a two-dimensional phase diagram on a two-dimensional paper. Okay, so what do we do? Suppose you are at this temperature, we have taken water in a beaker or in a test tube, whatever, water, and you are adding phenol. What do you see? At first there is only one solution, one unsaturated solution of phenol in water. Okay, you keep the temperature constant and you go on adding water into phenol, and when you reach here suppose point, this is C, suppose point A, what you find? You find two solutions. One is very important. Here at this temperature and at this phenol composition you find two different solutions. One is saturated solution of phenol in water and trace amount of very little, it is starting to form only very trace amount of water in phenol. Okay, and you go on increasing. Students, feel free if you have any questions. Okay, feel free to ask me. And you go on increasing phenol into it. What you find? You find two different solutions into different layers. The only thing that you notice is that amount of the solution, saturated solution of phenol in water is increasing, and the amount of saturated solution of water in phenol, amount of saturated solution of phenol in water is decreasing, and amount of saturated solution of water in phenol is decreasing. Like this, first you have, suppose in this test tube you have this amount of phenol, saturated solution of phenol in water, and a very little amount of saturated solution of water in phenol. You go on adding. Okay, what you see? The amount of the phenol in water is decreasing, and the amount of saturated solution of water in phenol is increasing. And you know, from the lever rule we can tell the relative amount of the different solution. So what is different? What is actually the change you are finding? The only change is the amount of the two layers as you go on increasing phenol into water. But there, at the same time, I have not yet discussed it, but it's will be told right now. That is, what is the degrees of freedom in different parts. Degrees of freedom you can calculate from your knowledge of the previous classes. Degrees of freedom is here 2. And when two solutions, we say conjugate solutions. We say conjugate solutions. When there are two conjugate solutions inside this curve. So inside this curve, the degrees of freedom is equal to 1. Here 2. So when temperature is fixed, you are going on adding phenol. The composition is also fixed because the degrees of freedom is only 1. As the degrees of freedom is 1, you go on adding phenol into water. You are getting two saturated solutions. Solutions of phenol in water and solutions of water in phenol. The compositions, the mole fractions of water and phenol in the two layers are the same because degrees of freedom is 1 and temperature is constant. So composition is automatically constant. Okay, and composition is given by this is called tile line at the end. This is the composition. This is the composition of phenol in water. Percentage you are getting. From this you are getting again the percentage of water, solution of phenol in water, solution of water in phenol. What happens here? When you reach this state, suppose B, what happens here? When you reach this state, what happens here? When you reach this place, you find saturated solution of water in phenol and a trace amount of saturated solution of phenol in water, and you go on adding phenol into water. What you get? You get unsaturated solution of water in phenol. So this is the sequence. When you come from C to suppose here F, you are coming from one solution, one phase system, to two solutions, two phase system, again into one phase solution. Now my question to you is that, can you come from C to F? See, these are partially miscible. Why? Because they are miscible in some extent, and they are not miscible after that extent. That is why they are called miscible, partially miscible. And you see what I am telling you, you are coming from C, yes, C, one solution, one phase system, to another F. And what you are experiencing, first you have one phase system, then two conjugate solutions, two solutions, then again one solution. My question to you is that, can you come from C to F without experiencing two solutions? Yes, you can come. What do? You increase the temperature to that point. Suppose this is G. Then you go on adding phenol into water until this composition. You come to this H, the same composition as F. Then you decrease the temperature to F. So you can come from C to F without experiencing two phase systems. You can come. So this is one point. Another thing that is important, see, this is an example for this. These are examples where you see this type of curve, and this is the case for phenol water, hexane, and so many systems are there. Okay, see, this is the point that is called critical solution temperature, above which, in this case above, there are cases there will be below. In these cases, for water phenol and water phenol like systems which shows large deviations from Raoult's law, I will discuss in our subsequent classes also. You see, after a temperature, above a temperature, phenol and water are miscible in any proportion. You get only one phase system. Degrees of freedom is 2. So this temperature is called critical solution temperature. Now you take the system at here, suppose O. You keep the percentage of phenol in water constant, you go on increasing the temperature. You go on increasing the temperature. What will happen? The system will move vertically. Okay, and what will happen, I am telling you, what will happen, the amount of phenol in water will increase and water in phenol will decrease, and we reach this and you reach here. This is called mutual solubility temperature, MST, mutual solubility temperature, where you are again getting a saturated solution of phenol in water and trace amount of water in phenol. And CST is the highest of all MSTs. CST is the highest of all MSTs. Why such things happens here? Because you see, with the increase in temperature, mutual solubilities increases. What happens? When you increase the temperature, there are cases like water in phenol where mutual solubilities increase. When mutual solubilities increase, what you see? What you see? You see this type of curve, upper CST. And there are cases where the mutual solubilities decrease with increase in temperature. There you find the curve of the diagram just opposite to that of this. And that is the case of water triethylamine, where you see a lower CST, below which that is 18.5. Just a minute. Water triethylamine, where 60.5 probably. This is for phenol water system 65.9 and 34 points. Composition is 34.4% of phenol. Water in triethylamine. You see here that you see the reverse of the phase diagram of phenol water system. In case of phenol water system, the mutual solubilities increase with temperature, and when the mutual solubilities increase with temperature, you get this type of diagram, and when mutual solubilities decrease with temperature, we get the just opposite of this diagram and this type of diagram. This is called lower CST, lower critical solution temperature, lower CST, critical solution temperature. And there are also, see, where do you get this type of thing? You get this type of thing for hydroxy compound and amine, or hydroxy compound keto type of system, because there is a hydrogen bonding. With the increase of this hydrogen bonding facilitates ki bolo solubility, and with the increase of temperature, hydrogen bonding breaks, hydrogen bonding breaks, and there is a decrease in solubility. And there are cases where after some time, with increase of temperature, solubility, mutual solubility is decreasing, but after some time it follows the general trend that it again increases with temperature. And for those systems, you get a loop-like of system. This water nicotine system. (208 degrees centigrade, 18.5 degrees centigrade), where you get both upper CST and lower CST. That is, you are getting one phase system above 208 degrees centigrade and below 18.5 degrees centigrade. Okay, so this is the case for water nicotine system, where after initially mutual solubilities decrease with temperature, after some time it again increases with temperature. So you get both like water phenol system upper critical solution temperature, and for water nicotine system, water triethylamine system, lower critical solution temperature. Okay. See, there is another interesting phenomena, that is, if we take the phenol water system or systems like phenol water system, suppose here or anywhere here, so here, and you go on decreasing the temperature very slowly. So what happens here? When the system reaches this point, a two-layer solutions start forming, and those two-layer solutions, particles of those two-layer solutions scatter light, and we see blue opalescence. This is called critical opalescence. What is called? This is called critical opalescence. That is, you take the system here above CST, you go on decreasing the temperature, and you do it very slowly, and when you reach this point, different layers start forming, and those layers, when they are just about to form, those layers, what do they do? They scatter the light, and you see beautiful opalescence, that the radiation from opalescence, and that is called critical opalescence, and this is a very beautiful phenomenon. Okay, see another interesting thing. Effect of pressure on CST and effect of impurities on CST. You must know what is the effect of impurities of CST. See, effect of impurities of CST is very great in case of these systems. When the impurity, please listen very carefully. When the impurity is present in only one solution, what it actually does? It decreases the solubility of another in their solvent. ভাবুন এটা, তুমি একটা সলিউশনের মধ্যে ঢুকে গেলে, তাই না? তাহলে তুমি কি করবে? তুমি ওর সেই সলিউশনের মধ্যে যে সলিউট আছে সেই সলিউটের কি সলভেন্টের সলিবিলিটি কমিয়ে দেবে। তাহলে if the impurity, you are adding impurity from outside into the phenol water system, suppose here, or any partially miscible liquid pairs, you are adding impurity from outside, and what you do? What you see? When the impurity is present in only one liquid, suppose you are adding KCl into phenol water system, KCl is soluble is only in water. What will do? It will decrease the solubility. It will decrease the mutual solubility, and when the mutual solubility decreases, what do you see? You see the increase in the CST upper, because the curve will be like this now, then the curve will be like this. Okay, curve will be like this, and you see the increase of critical solution temperature. And when the impurity is soluble in both the liquids, suppose you are adding impurity in such a way, in such a manner, or you have chosen the impurity, this is your choice only. Okay, the impurity is soluble in both the liquids, it will act as a cementing force between these, and it will ultimately increase the mutual solubility in both the phases, and the net effect will be lowering of critical solution temperature. So the impurity, please listen it, when the impurity is soluble in one phase, the mutual solubility decreases, so CST, upper CST increases. That is what we are emphasizing on water phenol system. So in case of water phenol system, the CST will increase, and when the impurity is soluble in both the phases, then CST will decrease. What is the effect of pressure on CST? Very important thing, very interesting also. What is the effect of pressure? What happens if you apply pressure? What happens? Mutual solubility increases, and when the mutual solubility increases, what happens? Upper CST will decrease and lower CST will increase. When you apply pressure from outside, what happens? First you find out what happens to solubility increases, and when the solubility increases, what will be? This curve will be like now this. Okay, and this curve will be like with this. So what will happen? Upper CST will decrease and lower CST will increase, and you go on increasing the pressure in case of water nicotine system. You go on increasing the pressure. You go on increasing the pressure, and in case of water nicotine system, the upper CST is decreasing and lower CST is increasing. You go on increasing the pressure. What will happen in water nicotine system? At a pressure, there will be only 1 point. Only 1 point, because this is decreasing. Area is decreasing. This is increasing. Area is gradually decreasing. And a time will come when you see only 1 point. The remaining everything is kibolo one phase system. So this is the effect of pressure on critical solution temperature. See, at the same time, one very interesting thing. What happens, though many liquids have upper critical solution temperatures, we do not generally see experimentally. We generally do not observe those critical solution temperatures. What is the reason? The reason is, actually, without high pressure, in most of the cases, we do not see upper critical solution temperature. Why? Because in most cases, upper critical solution temperature is greater than the boiling point of the liquids. So before you attain CST, they vaporize. Before you attain CST, they vaporize. So at high pressure, when boiling point decreases, only then you can experimentally find the critical upper solution temperature for those systems. Similarly, suppose the case of water ethyl acetate, water ether system. The critical solution temperature for such systems you cannot find out experimentally, though they have lower CST. But you cannot find out lower CST for those systems. Why? Because lower critical solution temperature for those systems is below the freezing point of the liquids. So they freezes. Before you achieve lower CST, they freezes. So where the boiling points are lower than the critical solution temperature, for those cases you never find upper CST, and where lower critical solution temperature is lower than the freezing point, you do not get what? Lower CST. This is all about phenol water system. I have very briefly tried to give everything in this class, and thank you for attending this class with utmost concentration. Thank you everybody.